If
P
property P is satisfied, then this condition must hold, right? Sufficient is the other way around. If the condition is satisfied, then the property holds. So here we'll say, okay, if it's stabilizable, so here we have U of x, so it's a map from Rn to Rm, is also C1, differentiable feedback. Okay. If the property holds, which is stabilizable, which means that x naught is asymptotically, just the definition of stabilizability, asymptotically stable equilibrium of the closed loop system. What's the closed loop system? Is x dot equals f of x, and you substitute by your function here, right?
Does it have to be locally or?
Yeah, this is asymptotically means locally. If you want to say globally, you have globally before. So x naught is asymptotically stable equilibrium of this guy, then the condition must hold, right? What's the condition? Actually, three conditions. So the first two to make it self-contained. The first two are obvious. What? The linearized part, like we said it in our discussion. The linearized part.
Has to be stabilized.
What?
Has to be stabilized.
The linearized part, if it's stabilizable, then we're done.
Oh yeah.
But the uncontrollable modes, they can't have eigenvalues in the right half plane, right? So the linearized part, maybe, yeah, has no, the uncontrollable linearized part has no eigenvalues in right half plane. So like the real part of the eigenvalues of the AUU after you linearize must be what? Must be what?
Less than or equal to 0.
Very good, less than or equal to 0, right? If it's very subtle here. If it's less than 0, we're done, right? If it's less than 0, then the linearized system is stabilizable, and stabilizable the non-linear system is true, right? The tricky part, if it's 0, if one of them is 1 or 2 or zeros, then okay, we don't know, and we are okay. Then the second part, please pay attention here. There exists a neighborhood n of x naught such that what? Yeah, for all x in the neighborhood, there exists a control input history. So u is a function of time. And for any x, so I will parameterize this by x. This is a function of time here, so it maps 0 infinity over time to Rm that steers one from this point x at time 0 to the equilibrium as t goes to infinity. Please take your time to digest this. So here is x naught, your equilibrium. We require the existence of a neighborhood such that for any point in that neighborhood, for any point x in that neighborhood, I have a control that sends me here. Do you think this is too stringent? Do you think this is the definition of stabilizability? What's the stabilizability? I want to go, so for any point in the neighborhood, stabilizability, I want to make it stable by control, right? What do you mean stable? Stable that in a neighborhood, any point here I can go to the equilibrium. And I want to do that by control. Is this equivalent to stabilizability? Because if it were, then this is useless. I cannot say a necessary condition for stabilizability is your system must be stabilizable. I mean, it can't work, right? Is this equivalent? It seems that it's equivalent to, it seems, right? Equivalent to stabilizability. Is it? Aside from the fact that Brockett is a great name and he will not do that. Aside from that fact. Is it equivalent to stabilizability?
So this is steering. It doesn't have to stay there, right? Or
No,
If by getting
it's steering,
there.
but if it's equilibrium, then it will stay there, right? Yeah. What do you think? It's a very important concept in control, which is obvious if you think about it. Oh, for sure. Why? Because are you interested in the following? We have an airplane, and for any given disturbance, this is cruise, and for any given disturbance around the cruise, I give you elevator deflection that will get you back. Elevator deflection is a function of time. Are you interested in that as an engineer? Elevator deflection is a function of time for any disturbance. So I promise you, if you give me a disturbance, I'll give you elevator deflection as a function of time. Is this a good solution?
No.
We're never interested in that. Why? Because this is an open loop. I need a smooth, aside from the fact it's smooth, I need a closed loop, right? I need a magic formula, because the open loop requires exact knowledge. You can always do open loop control, but it requires exact knowledge of the system dynamics. You require that you know this dynamics super well. If there is anything missing, then you will be off by far. You will not be able to correct. But the closed loop, the feedback, right? The feedback control law, this is a control input history is a function of time. It's not feedback. This is a feedback control law. They have different naming, okay? So the feedback is a magic formula that even if you have imperfections here of your knowledge of the system or whatever, or even if you have, the environment changes, I don't care because I measure X. I measure X and feedback in my control law, so it corrects itself. So this is not equivalent to stabilizability, right? The stabilizability is much more. This is indeed something like small-time local controllability that you can steer. So you give me some input history as a function of time that will steer me to X naught. This input history might be something like that, right? So it might be in patches. It's a legitimate control input history that is piecewise continuous. All of the requirement of mu is just piecewise continuous. And it will steer you here, but you cannot patch it together such that it becomes a function of the states.
Can
You see what I'm saying?
can it go outside the neighborhood and come back, or no? It has to be inside the neighborhood all the time.
That's a good question. Here, it doesn't say that it has to stay. It can go outside. But what I'm trying to say is that even if it stays inside, this is not so useful because what we described and why, okay, these are different, but why they are not equivalent mathematically? Because this control input history might be very weird, so that along that path, along all the paths, you cannot be written as a function of x. Okay. So use a function of time, yes?
But it's stating the obvious literally, right?
The what?
This condition is stating the
Yes, it's like this, but for completion, like I said. Yes. Now, it's obvious, but when you see it the first time, it looks like it's.
So there's nothing beyond this.
There's nothing beyond. There's nothing beyond. This is small-time local controllability. The main thing that we get here is that small-time local controllability does not imply, because there is still a third condition, which is actually Brockett necessary condition is usually the third. These are just for completion. Small-time local controllability does not imply stabilizability. Okay? So you can have a controllable system, but you cannot stabilize it. Why? Because stabilization, we're talking about feedback. Yes, if you have a controllable system, you can steer it as a function of time, input as a function of time, to your equilibrium, but this is not useful for engineers. We need feedback control law. Okay? And now I'm about to state the meat of Brockett necessary condition. Some people, when they refer to Brockett necessary condition, they refer to number 3. Any questions so far? These are obvious requirements for sure. Any questions so far? The map F as a map from XU to X dot, okay, is onto an open neighborhood of the origin in Rn. So it takes here a pair XU and gives you a point in Rn. It's not actually a point, but it's okay. It's a vector, right? But it's okay. A point in Rn. This map should be on 2. probably you have forgotten what you mean by onto, so you're just trying to, this is a map, right, F, and we have points here, we have points there. So this map which I'm drawing now is onto i.e. it covers all the points in the range. This is onto. Surjective. It covers all the range. This is not onto. So there are points that are left out. Not onto. So onto means what? That for any point here there is a pre-image. It means that any point here can be written as f of something over there, right? Okay, how do you prove onto? I mean, if I give you a function and I ask you how to prove that it's onto, how do you do it mathematically? Like I said, any point here can be written as f of something over there. That the map f of x and u is equal to y is solvable in y, right? Solve it for any y, get the corresponding x and u, then it means that any y can be written as this guy, right? Solvable in y.
This is the implicit function.
What?
The inverse function here.